Let's do an exercise and try to find the correct type class constraints for a number of functions Haskell has in its Prelude. You don't have to define the implementation, just try to calculate what the type class constraints would be. For reference, here is the type class hierarchy, which you may find handy to refer to. The first function is sum, which takes in a list of any type and returns that type. The idea is that it would return the sum of all items in the list. What should the type class constraint on the function be to make it the most generic possible? If you guessed num, then you are correct. The num type class has instances of int, integer, float and double, and so covers all of the relevant type of numbers we want to sum over. But why num over real? Real has instances for these types too, doesn't it? Well, because the real type class expects instances to be ordered, since it has a constraint that its type must implement the ord type class. This is an unnecessary constraint to put on our sum function, since we do not need arguments to be ordered to calculate the sum. The second function is maximum, which again takes in a list of any type and returns that type. What should the type class constraint on this function be? If you guessed ord, then you are correct. In the most general sense, the maximum can be found for not just numbers, but also for other types which have a natural ordering, such as for characters. By requiring that the type have an instance of the ord type class, we make sure that there is a clear way to compare items in the list, and so we can extract the maximum through comparisons. And now we have another function called product. This is supposed to calculate the product of all items in the list. What should its type constraint be? For the exact same reasons as for the sum function, the type constraint is num. And finally, we have the minimum function. What should its type class constraint be? Just like for maximum, its constraint is ord. I want to take a minute to explore another interesting thing which we can do with type class constraints. Let's look at this function. All it does is take in an int, and if it is 0, return a string which says it is 0. Otherwise, it returns a string saying not 0. If we try to compile it with this function signature, we end up getting a compilation error which looks like this. The error says that for the pattern match f of 0, it is unable to find the EQ type class from the signature. If you remember, I mentioned it before. The GHC compiler since version 7.4.1 no longer follows the Haskell language specification for the num type class. According to the hierarchy, this should work because num is a subclass of EQ, but in GHC that is not the case. To fix this, we can follow the suggestion given in the error message and add the EQA constraint to the function signature like this. Since all of the types which have instances for the num type class also have instances for the EQ type class, this works. In this case, we are adding more than one constraint to the signature. In fact, you can add as many constraints as you need. I wanted to be sure to show this to you before moving on. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the LigoLearn channel. See you next time.